Today's topic is equipotential surfaces and their properties. As from the word equipotential, the literal meaning equi means equal, potential is the potential. So equal potential at all the points of any surface. Such surfaces are called equipotential surfaces. For an example, as we know that potential for a point charge V is equal to 1 upon 4 pi epsilon naught Q upon R. That means V is proportional to 1 upon R. So if we take a point charge, then these points, they all are at the same distance R. So we can say that the potential at point A, B, C, D, E, F. All these points, they are at equal distance. So these points will have the same potential. Now if we join all these points, then we obtain a spherical surface. So for a point charge, the spherical surface will be known as the equipotential surface, whether it is a negative charge or positive charge. The equipotential surface will be the spherical. The difference between the positive and negative charge, as already told, that for positive charge, these are the electric field lines, so these are outward, and for negative charge, these electric field lines will be inward. Now if we consider the uniform electric field, this is uniform electric field directed towards the right. Then all the planes, if the electric field is directed towards x-axis, then all the planes in yz plane, all the surfaces in yz plane will be the equipotential surfaces. Now let us discuss some properties of the equipotential surfaces. The first property is no work done in moving a test charge over an equipotential surface. That means if we move a test charge on any surface, then work done will be 0. To understand it, let us consider an equipotential surface. So this is an equipotential surface on which these are the 2 points A and B. Since this surface is an equipotential surface, so potential at point A, VA, that will be equal to potential at B, that is B. So VA is equal to VB. So if we move a test charge from A to B, then work done, WAB, will be given as Q0 VA minus VB. Or since it is potential, so that will be VB minus VA. So if we move a charge from point, then the work done will be equal to Q0 is equal to VB minus VA. Since VB and VA both are equal, so this work done will be 0. So we can say that potential on moving a test charge on any equipotential surface will be 0. The second property is the electric field is always normal to the surface at every point. That means this surface will be normal to the electric field will be normal to this surface. Now to explain or to understand it, let this electric field is not normal to this surface. It means at this point, this electric field will make at an angle to the surface. Now when it is making an angle, then it will have the 2 components, one component perpendicular to it, another component along the surface. Now because of this component of the electric field which is along the surface, some work has to be done in moving a charge from A to B against the electrostatic force due to this electric field. But as we have explained earlier, that work done is 0 in moving a test charge on any equipotential surface. So it means no question arises for the existence of this tangential component. In other words, we can also explain it that work done is equal to 0, and we know that work done is equal to force into displacement, that is the dot product of force into displacement, and force into displacement is FDR cos theta. Then work done is 0, then either F is 0, dr is 0 or theta is 0. In neither condition F and dr 0. So it means only cos theta is 0, and when cos theta is 0, it means theta is equal to 90 degree. That means the angle between force and displacement is always 90 degree. That is, electric field is normal to the surface. So electric field is always normal to the surface at every point. Now the third property is electrostatic fields are closer together in the region of strong field and farther apart in the region of weak field. Now this can be explained that as we know that V is equal to minus dV upon dr, or we can say that dr is equal to dV upon E. So for the same change in electric potential, that is when dV is same, then we have that dV is equal to constant. So we have from here dr proportional to E. So we know that electric potential is the negative gradient. E is equal to minus dV upon dr. So from here dr is equal to minus dV upon E. For the same constant potential, equipotential surface means dV is constant, then dr is proportional to 1 upon E. It means if the lines dr is small, then E is larger. So electric field is stronger where the equipotential surfaces are closer to each other, and electric field is weaker when the equipotential surfaces are farther apart. The next property is no two surfaces intersect each other. If two equipotential surfaces intersect each other, then at the point of intersection there will be the two values of the potential at the same point, which is not possible because the two different equipotential surfaces, they are intersecting each other. So suppose we have one surface whose potential is V1, another surface whose potential is V2, but these are itself equipotential. This is also equipotential surface. Now if these surfaces, they intersect each other, then at the point of intersection there will be value according to this V1, the value should be V1, and according to this surface the value should be V2. So at the same point it is not possible that V1 and V2 two different values can exist. So in other words, we can say that no two surfaces intersect each other. So at last, let us revise or summarize what we have studied in this video. That equipotential surface means the surfaces which are having the same potential at all the points. Work done in moving a test charge over an equipotential surface is 0. Electric field is always normal to the surface at every point. Equipotential surfaces are closer together in the region of strong field and farther apart in the region of weak field. No two surfaces can intersect each other. Thank you.